Hello and welcome to a very special edition of Midterm, Mr. Viola's Physics Classroom. Today we're going to go over all the topics and all the things that are going to be important for your midterm exam. So it's basically over the entire first half of the year. It'll be 50 to 60 multiple choice questions. We're going to start with unit conversions. So at the very beginning of the year we talked about unit conversions. So we started with our base unit, whether that was the meter, the liter, or the gram. Remember, it could be either one. And then we would convert to units, either powers of 10 higher or powers of 10 lower. So if we were going up, we talked about deca, hecta, and kilo. And if we went down, we talked about deci, centi, and milli. So when we were moving up and down this chain, we were really just moving the decimal around. So if I took something like 450 decaliters, and I wanted to convert that to centiliters perhaps, I looked at how far I moved along the continuum. I went 1, 2, 3 places to the left, which meant that my decimal, which is right here, would move 3 places to the right. So instead of 450, I move 3, plug in my zeros, and I end up with 450,000 centiliters. So again, we're moving decimals, we're moving spots along this, we're changing our prefixes, but the number is not really changing. So I still have the 450 I started with, I added my zeros to account for moving down, and I ended up with 450,000. If I go the other way, so if I started with something like 300 millimeters, and I want to go to maybe all the way to kilometers, we go 1, 2, 3, don't forget to count the base, 4, 5, 6 places to the right, which means my decimal point's going to go 6 places to the left. So instead of 300, I'm going to go 1, 2, 3, 4, 5, 6. Fill in my zeros everywhere I have a dip. And we end up with 0.0003 kilometers. This was the first thing we did on the year. It was all about converting units between different metric prefixes. We'll do one more just to make sure, and then we'll move on. If I have, well, we've used the liter and the meter, so let's use the gram. If I have 2.65 hectograms, and I want to change that to, let's go right to the base unit, let's go right to the gram. I'm going 1, 2 places to the left, which means my decimal needs to move 2 places to the right. So instead of 2.65, that decimal moves, and I have 265 grams. So moving units, or changing units, moving decimal points, up and down. These are the kind of questions you get. It's all multiple choice. I would give you some options that would go with, like for this, I would probably give you 26.5, 265, 0.265. So you really have to know how many places you're moving and what that does to the decimal. I would suggest writing these things down on your note card if you don't remember them. Remember, your note card can be back and front, a 3x5 note card that you're allowed to use both sides of. You can write as small as you want. You can type it if you prefer. You can even do size 1 with a magnifying glass. That's fine. So unit conversions, pretty straightforward. We're done with those. Dimensional analysis was the second thing we did this year. It was really a spin-off of unit conversions. We took mostly an English to metric conversion. So something like if I said 250 kilograms and I wanted to go to pounds. And so I wonder how many pounds that is. Well, I don't know how many pounds that is off the top of my head, but the conversion that I know, and one that you may want to write down, is that 2.2 pounds is equal to 1 kilogram. You may also want to know these following conversions. 5,280 feet is 1 mile. You may want to know that 2.54 centimeters is 1 inch. You may want to know that actually you should be pretty good with those 3 conversions. You're welcome to write down anything else that you want on that note card, but again, these ones will probably suit you just fine for what we're doing. You need to, of course, know how to go to convert units, maybe from kilogram to gram, perhaps from the centimeter to the kilometer. But if you know these, your problems might be fairly long, but you'll at the very least be able to solve them. So going back to the one we were just doing, if I want to go from kilograms to pounds, I start with 250 kilograms. Whatever unit is here needs to go on the bottom. The unit I'm going to goes on the top. We just said that there's 2.2 pounds in 1 kilogram. So I would take 250 and I would multiply by 2.2. Now 250 multiplied by 2.2 is 550 pounds. The units cancel out here. Whatever's on top is what I'm left with. And so, pretty simply, we can see that this unit being here and this being here are our important parts. Remember, the numbers that go in here are the conversions. 1 kilogram is equivalent to 2.2 pounds. I could have one that's slightly harder. If I had something, I don't know, instead of this, maybe I was trying to go from miles to meters. Something like 20 miles, and I want to go to meters. Well, let's say I don't know how many meters are in a mile, but I know how many feet are in a mile, and I know how many inches are in a foot. We'll continue down here. I know how many centimeters are in an inch, and I know how many meters are in a centimeter. This is my setup. I get my answer in meters at the end, so we'll put that right down here. There is 5,280 feet in 1 mile. There are 12 inches in 1 foot. There is 2.54 centimeters in 1 inch. And in 1 meter, there are 100 centimeters. So now, I'm going to take everything I've done, I'm going to multiply across the tops, and divide by all the things on the bottom. So let's see, 20 times 5,280 times 12 times 2.54 divided by 100 gives me 32,186 meters. So this was more than 1 step, it was 4 steps. If you have a note card and you have extra space, maybe you have a miles to meters conversion that you could make this a 1-step problem. Completely up to you. At least you would want to make sure that you had this conversion on there so that you could get from the English system to the American system to the metric. So you will not have a ton of problems like that. They're lengthy. So we have an hour and a half to do the exam. So it can't give you more than a few. So dimensional analysis, I'm checking off. Speed and velocity. This was our first major unit. It started with what the difference was. So speed, remember speed is a scalar. Scalar just means it doesn't have a direction. It can't be negative. Speed's like when you drive your car. You can go 40 miles per hour, you can't go negative 40 miles per hour. So the equation for speed was distance over time. I'm going to travel a distance. It's going to take me a certain amount of time. If I divide them, I get the speed. The thing to keep in mind is that distance over time is not the same as displacement over time. Distance, again, is a scalar quantity. It doesn't have a direction. I can't have a negative distance. If I'm finding distance, I'm simply adding up everything I've done, all the things whether I'm walking or driving, all the distances, and that is my total. Conversely, if I'm finding velocity, velocity is a vector quantity. It has a direction. So velocity, similar to speed, but instead of distance, it's displacement. Displacement is also a vector. It has a direction associated with it. It can be negative. Velocity can be negative. I can go negative 40 meters per second because it's just denoting the direction that I'm heading in. All a negative sign is doing is telling me direction. It's not telling me anything about the value or the speed that I'm going. So we have these two equations. The one that we have focused on most was the velocity equation. And we had V is the change in position over time. This is what I would suggest you write down on your card. If you prefer to have it written out completely, feel free to write down the blue and the green. This will be enough for you though, as long as you know that delta x is change in position or the displacement. It wasn't just equations that we did with velocity though. We also did a lot of graphing. And so one of the pieces of graphing that we did was we did a lot with finding the slope. So we had a lot of position and time graphs. And many of them looked like this. And when I have a position and time graph, the slope of that is the velocity. So if I find the slope of a position time graph, I have found the velocity. So this velocity would be positive and it would be constant. The slope is not changing during this entire time interval. If I have something different, so perhaps instead of a straight line or a diagonal line, I have a perfectly straight line. The slope still is the velocity. This person's not moving though, or this car is not moving, or whatever this is not moving. So my slope is 0, which means my velocity is 0. The last one, or it's not the last one, but another common one, if I have a curve, anytime you see a curve on any graph, you can think I'm accelerating. I'm moving faster and faster, or I'm going slower and slower. The slope still stands for the velocity, but because it's curved, it's a changing slope. So the velocity is changing. In this case, I'm going faster and faster. This one in orange is going slower and slower. I'm covering less ground in a greater amount of time until eventually I come to a stop over here. So you could have either of those. Those are both positive slopes, so you have a positive velocity. If I was coming like this, I would have a negative slope, and I'm slowing down, so I'd have a negative velocity. The same thing if I had something like this. I'm speeding up, but I'm doing so in the negative direction. So there were a lot of options of what you could have on a position versus time graph. Also keep in mind, we made several graphs during the first semester. Let's fix that. That looked like maybe they had more than one line. And so the important thing on this is that you should be able to tell which one is going faster. And in this case, we'll label them here. Line A is going faster. Whatever's making this graph is going much more quickly because it has a greater slope. The greater the slope, the greater the speed. Once we mastered the position time graphs, we moved on to velocity time graphs. So we have time and we have velocity, or velocity in meters per second. And so in this case, the graph, what the graph is telling us has changed a little bit. If my line looks like this, or however it looks on this graph, once again the slope is giving us some information. The The slope in this case is telling us the acceleration. So in this case, I have a constant positive acceleration because I have a constant positive slope. The extra piece of information this graph tells us is that the area underneath the curve is the displacement. So if I find the area between this line right here for the x-axis and the line that I've made, that tells me the displacement of whatever is going at that velocity. So if this is a car that's increasing its speed, I am covering a greater and greater displacement, covering a greater distance as I go. So I can get that from this graph. Now, anytime this graph crosses the x-axis, this means this is the spot that I've stopped moving. I had a positive velocity, I slowed down, I stopped moving, and then I started to speed up in the negative direction. So even though I'm below the x-axis, I'm still speeding up, just in a different direction. So to recap, if you're looking to write down some equations, velocity is change in position over time. We have graphically shown it, we showed it mathematically, we did a lot of labs with it. If you have old labs, you should probably look at those. The buggy common assessment was based on this equation right here. So speed and velocity, check them off the list. Acceleration. Acceleration, we had our equation, change in velocity over time. This was our basic equation. For the honors class, you had 3 more equations. They were our constant acceleration equations. This was our first one. And this is our second and third one. And so these are different in slight ways. In our first one, if you're solving for position and you have the time, this is probably your best equation to use. The second one is handy because it doesn't involve time, so if you weren't given the time, you can still solve for different variables, either velocity, acceleration, or position. And the final one is the most basic, it's the easiest to work with, and it involves the final velocity, which the first one doesn't. Remember, if there's a little initial symbol, little 0, sub-zero, it means initial. It's the original time, the original velocity, the original position. So these are things I would probably write down on my note card if I'm in the honors class, because it's a lot to memorize. So these were our 4 major equations for this section. The other thing we did during this point, or during this unit, was we talked about g, the acceleration of gravity, being 9.8 meters per second squared. That's another important part of this. If anything in free fall, it doesn't matter what the mass is, anything that's free falling in a vacuum is accelerating at 9.8 meters per second squared. So we want to make sure that that's something. This may be something that you've memorized, no need to put it on the note card. So apart from the velocity time graph that we just drew, the last type of graph we had was acceleration versus time. And this graph was always either a flat line above the axis, a flat line below the axis, or at the 0 mark. We either had a constant positive acceleration, a constant negative acceleration, or no acceleration. Those were our only 3 options for everything we've done so far. The next major thing we did was forces. We force diagrammed a lot of different situations in this quarter. So we have different types of forces that include normal, which is something that is pushing back up on an object. If you're on a hill, it's pushing at an angle, but it's always something that's kind of working against gravity. Gravity is our second one. It's always there, no matter where you are, as long as you're on planet Earth, you have gravity. Drag. If you are in water or falling through air, there's going to be a drag force on you. Tension. If you're hanging from a rope, or you're hanging from a cord, or you're hanging from whatever it is, the object is hanging from it, there's a tension force that's holding it up. We also had an applied force, which is basically a push or a pull. If there is nothing pushing on or pulling on, there's nothing physically applying a force, this is not part of your force diagram. We had the force of friction. Anytime something is moving, there's a force of friction on it, unless specifically stated to ignore friction. Oftentimes we'll ignore drag, rarely we'll ignore friction. We did a lot of work with friction. The ones that we really did a lot with, I thought, were friction, gravity. But really the two. There are equations for those two. We have gravity is mass, always in kilograms, times g, which as on Earth is always 9.8. And for friction, we have the force of friction is the coefficient times the normal force. The coefficient is always between 0 and 1. The closer to 1 this gets, the larger the amount of friction. The closer to 0, the lesser amount of friction. The normal force is often associated with gravity. They're equal and opposite usually. Not always. If you're on a hill, they're not equal and opposite. On flat surface, they're equal and opposite, so we can use mg for that. And then the force of friction is often opposite an applied force, or maybe opposite nothing if you're slowing down. Remember that Newton's second law, the net force is mass times acceleration. Unbalanced forces mean I have acceleration. I'll repeat. Unbalanced forces mean I have acceleration. Balanced forces mean I have either no velocity or a constant velocity. So if I have something, a book on a table, that's not moving, I maybe have this. They're equal and opposite, the book is not moving, there is no net force, there's no acceleration. Now if I start to push the book at a constant velocity, I'm applying a force, friction is now applying a force in the opposite direction, they're equal and opposite, I have no acceleration, I have no net force. If I push the book harder and cause an acceleration, now I have more applied force than I have force of friction, which means I do have a net force, and unbalanced forces mean I am accelerating. So if you're drawing a force diagram, or perhaps you're answering an explanation for a situation a force diagram could be drawn for, if I have unbalanced forces, somewhere something needs to be accelerating in the direction of the unbalanced force. We talked a little bit about Hooke's law, so elastic force, and this idea of a spring constant. So a spring constant can be between any two numbers, it can't be negative, so between 0 and infinite. This is how far the spring is compressed, and then this is the force of that spring. When we did the lab, we had a setup with a spring, and then a weight on that spring, and the force of gravity was equal and opposite to the elastic force. And so we could set mg, mass always in kilograms, times 9.8, equivalent to our elastic energy, our elastic force, and then use that and the amount that it was stretched out to solve for k, which is what we did in that lab. You could be asked similar questions on the midterm. So forces, check. Last one, work and power. We just began this unit. We really only have two equations at this point. Work is force times distance, and power is work over time. The only tricky part to this, recall that the distance or the displacement and the force have to be parallel to each other. I'm pushing something, I'm putting a force on it in the direction it's moving. If I'm carrying something and walking, you're not doing any work because those are perpendicular to each other. Work is measured in joules, so work would be in joules. Power is measured in watts. So power is all about how quickly I do the work. If I do work very quickly, I have a high amount of power. If I do work very slowly, it's a low amount of power. Just like when we were running up the stairs, you got closer to a horsepower if you ran up quickly, and then your mass also played a pretty important role. So 1 horsepower is 746 watts, which maybe also be something you want to write down in your card. So that takes us through basically the entire first semester with a quick overview of everything that we've done. Any questions, please stop in. Best of luck on your exams. I hope this was helpful.